Welcome to the interview, Professor Sauer. Now, you're a researcher and teacher with the RWTH Aachen University in Germany. You're the chair of the Electrochemical Energy Conversion and Storage System department. And we're going to talk today about solid state batteries. So welcome to the interview.
Yeah, thank you. It's my great pleasure.
So look, before we get into the details of solid state batteries, I want to run something by you because as an energy journalist, I've been interviewing battery scientists starting back in 2015. And from 2015 to 2017, they were telling me that, new electrochemical chemistries would come on board, maybe 2030, lithium air, lithium metal, solid state. Prices would drop maybe 50% by 2030. It was more of a gradual kind of evolution, a story arc. And now we see all of the things that were predicted in 2030 are actually have come true in 2020, 2021. And is that your sort of perception of how the battery technology has evolved?
I was also surprised by the speed, by the timeline where especially prices dropped. I was not surprised about the technology developments because at the end of the day, it was an evolutionary development. We're still with lithium-ion batteries, but we should be aware that maybe different from battery technologies we have known for a long time, like lead-acid batteries or nickel-cadmium batteries, there you really have just no choice of different materials. You have lead dioxide, you have nickel and cadmium, but in lithium-ion batteries, 2.5% of the weight is maybe lithium of a lithium-ion battery, and all the things around could be changed a lot. And what we have seen is changing in the cathode materials. Today, we're going towards 60% or 80% of nickel, so cobalt is reduced significantly. We have shares of 5 to 10% of silicon in the carbon already. So this is an evolutionary development within the same group of lithium-ion batteries. And this is what the state of the art today. Everything what is sold on the market is still within this.
A related question, Dr. Sauer, and that is that my impression again is that a lot of the that rapid evolution and changing materials and so on was because battery companies, automakers, other companies poured enormous resources into engineering solutions to some of these problems, and that maybe got us to where we are today quicker than we expected. Would you agree or disagree?
Oh yeah, absolutely. The large companies in Korea and in China, they put together thousands of engineers and scientists to bring things forward. And it's even difficult for us in science to keep the pace. Yeah? So when you look at what Tesla is doing, they are always bit ahead. Yeah, for sure, they also work with scientists and they bring in new ideas and concepts and so on. But we have to be aware that the biggest challenge anyway is bringing down the price. From a performance point of view, the batteries are anyway good as they are. Yeah? So we are talking about price. And this is quite similar to the photovoltaic market. If you look back within the last 20 years, the real step forwards in technology were quite low. The maximum efficiency did not increase too much, but what the photovoltaic industry was able to do is to bring down the price by a factor of 10 or something like this, yeah? Using much less clean raw materials and less processing steps and full automatization and so on. And at the end of the day, it's the price that matters. And this is also why it is so difficult for other technologies to enter into this.
Well, let's talk about solid state batteries. And maybe we could begin with a short description of a solid state battery compared to your current lithium ion battery design.
Yeah, so first of all, you have two electrodes, and the one we call the cathode, the other one we call the anode. The cathode, first of all, is relatively the same in a solid state battery, at least what is in the development and research today, compared with the lithium ion batteries. What is different is the electrolyte. We have liquid organic electrolyte today, which makes it relatively easy for the ions to travel during charging from the cathode to the anode side. And the solid state batteries here have either a ceramic or a polymer. In any case, no liquids, but solid state materials. This is why they're called solid state. And the traveling of ions in a solid state material is much more difficult, or in other battery technologies, you need high temperatures to have at least sufficient diffusion rate, and diffusion rate is proportional to power, to charging times, and so on. And then finally, on the anode side, today we have graphite, 10 times more graphite than lithium, just to have a safe material. The graphite itself does not contribute to power or to especially not to energy. It is just additional cost and additional energy. And the main idea of the solid state batteries is to get rid of this carbon, so 90% of the weight of the anode, and just replace it by a pure metallic lithium electrode. And this is what is difficult with the organic electrolytes, because lithium is so reactive that just with pure organic liquid electrolyte, it's not working. That was tried, but was not successful in the market.
So my understanding, my takeaway from what you said is it sounded like the solid state, the solid ceramic electrolyte, the ions don't pass through it as easily as through the liquid electrolyte. Did I get that right?
Yes, so this is the biggest challenge. For example, there is a battery type called sodium sulfur batteries or sodium nickel chloride batteries. They also have a solid state a ceramic separator. They are on the market since maybe 30 years, but they operate at 300 degrees centigrade. So at high temperature, which gives a lot of problems with thermal management, thermal losses, and so on. But this is necessary to make the diffusion rate sufficiently.
And the solid state batteries that are going to be coming on the market in the next few years, have engineers and scientists solved the problem of the diffusion rate of the ions through the solid material? Have we solved that problem?
Definitely, they made progress in this field, and so we see some samples of batteries. At least some data are published, which show sufficiently improved performance of the batteries. No doubt. However, personally, I have not seen data yet which really show a full battery cell design. The big issue is the distance between the cathode and the anode is relatively thin. So it can be maybe as thin as 5 micrometers or something like this. So the distance for the ions to pass through this distance is short. But if you want to have high energy density batteries, you need cathode materials with a thickness of maybe 100 micrometers. And this is what I haven't seen demonstrated yet. So it seems as most of the examples where we see data are very thin. And this works, but the energy densities are far away from what we have today with the lithium-ion batteries, and even more far away from what is promised with lithium-ion batteries, because this would require 100 micrometer thickness of cathode materials.
Does that mean that battery manufacturers are going to have trouble delivering on the promises we've heard in the media when they deliver solid state batteries in a couple of years? Are we going to see solid state batteries that outperform the current lithium ion batteries?
So first of all, also the solid state batteries are somehow it's a big step forward, but it's still also something like an evolutionary development, because we still have similar cathode materials, production processes in maybe 70% or whatever will be quite similar. So this is nothing which is totally a game changer from the production side and so on. But to be honest, I haven't really seen until now from the major car manufacturers real plans to come with solid state batteries until 2025 or even later. What we have on our test benches, and we're operating something like 2,000 test benches and working with all the at least German car manufacturers and several other international car manufacturers, there are no solid state batteries on our test benches at all. And when they come to our test benches, then it may take 3-4 years until they may be ready for the automotive industry. So there are some rumors, and there are companies, many of them venture capital driven, who have good news about the technology very often. But if you look to the plans of Tesla, if you look to even Volkswagen is talking about QuantumScape, but what they are doing in the development and research centers here in Germany has nothing to do with solid state batteries.
So fair to say that we're probably be looking at maybe between 2025 and 2030 for the introduction of a solid state battery in a production automobile.
But maybe, yeah, but maybe, because you know, you always have to be you always have to be aware as well that the existing technology also improves. Yeah, so this is a difficult hunt for getting better. And I just looked before we start talking today to presentations by QuantumScape, for example, and they compare their technology with what they call state-of-the-art technology. For example, they claim 800 cycles to end of lifetime is something very extraordinary. 10 years ago, we had batteries with more than 3,000 cycles commercially in the cars on the road. The cycle number decreased in between just because there's no need for higher cycle lifetimes. Yeah? So claiming for higher cycle lifetime is nice, but just imagine if you have a battery with 1,000 cycles and a driving distance of 400 kilometers, it's 400,000 kilometers lifetime driving distance. That's much more than the car will do. Yeah? So there's no need for more lifetime, for example. Or they claim they can charge batteries faster. In a quarter of an hour. The car manufacturers like Porsche, they are developing batteries for a charging power of 350 kilowatt. Infrastructure which is under construction in Germany. This is a quarter of an hour with the existing technology. So therefore, when the batteries are ready, we will see what the classical lithium-ion batteries will do until then.
Well, let's talk for a moment about the advantages of solid state batteries. So my understanding is that they're safer, so less flammable because they don't have a liquid electrolyte. They have a higher energy density, so we're going to get more kilometers per given battery. They have a longer life, and they charge faster. But it sounds like from what you just said about the current technology, that the current technology is maybe a lot closer to what solid state would deliver than we might have expected. Is that a fair comment to say?
Yeah, you know, all these advantages which you just have mentioned, let me say, to achieve them, it really requires to get to the limits as well. Yeah? And this is exactly what the lithium-ion batteries are doing since 20 years. Yeah? The technology, as we discussed, did not change too much, but we're going much more to the limits meanwhile. And I come back to the example with the thickness of the cathode. If we are not able to transport ions on distances of 100 micrometers through the active material, we won't get to the high energy densities. These high energy densities would need these thick cathode materials. But there's no question that the batteries could be more safe. Indeed, the organic electrolyte is more flammable. The carbon, the graphite in the batteries is also something which burns quite well. So they could be more safe. Also, the hope is that we can operate, or it's very likely, let me say, that we can operate them at higher temperatures. And this makes things easier, especially with regard to fast charging, for example, because we must not cool down the battery in the same way as today's batteries. So cooling is the biggest challenge maybe during fast charging, and maybe we can let the batteries go up to maybe 100 degrees centigrade or whatever just during the relatively short period of charging, and then temperature will decline anyway later on. So these are definitely advantages. With regard to the energy density, there we really will see if it will be possible to come on the market with batteries having these thick electrodes and therefore can get towards the high energy densities, which are theoretically possible, no doubt. Yeah, theoretically, they are higher, maybe by 30% higher or whatever, compared with the lithium-ion batteries.
Now, we've talked primarily about applications in the automotive market, but the other big one, of course, is in the utility market. So with renewable energies, wind and solar, and they're intermittent, and we're seeing more and more batteries adopted at utility scale. What kind of implications for utility scale applications are there of solid state and some of these innovations?
For the stationary batteries, first of all, the energy density is not really a major issue. So this does not bring advantage to the market for the stationary market, even more than for the automotive sector. Cost is the main driver. Because, as I said, weight and volume is not so important, and cycle lifetime. We have to be aware that in stationary applications where you can earn money, you would need, let me say, at least 3,000 cycles, more or less full cycles, to get economic somehow. And this is something we see in the last few years, that development for batteries for stationary applications and the automotive sector separates. So let me say in the last decade, manufacturers of batteries cells try to bring the same battery cells into the different markets to increase the production volumes, to gain the economy of scale effects. But meanwhile, the production volumes are so high that we can have economy of scale separately. And therefore, we will see different chemistries in different markets in the future. If the solid-state batteries could make it better than the today's lithium-ion battery, will depend mainly on the price and production on the one hand, and on the cycle lifetime. So we need, let me say, at least 3,000 full cycles.
So to wrap up, Professor Sauer, what would you say are the two top technical challenges that battery makers have to solve, and are they likely to solve them in the next, this decade?
I'm sure there will be lithium-ion solid-state batteries on the market. The question is, will we really see them in the mass markets in the automotive sector, or will we see them maybe in some niches or in some quite different markets? The main challenges are surely to produce batteries with energy densities comparable to what we have today at a price which is comparable. And this is definitely a challenge. And I'm not absolutely sure that these solid-state batteries will beat the, let me say, conventional lithium-ion batteries with liquid electrolyte by the end of the decade. At least for the automotive sector, I do not expect it significantly earlier. As I said, the other batteries improve themselves as well. They do not stand still with their performance. Look to the things which were announced in last September, I think, by Tesla, reduction in price until 2025 by roughly 50%. And these are very realistic, let me say, master plans, because each step they have announced is relatively well known how to do it. Yeah, and each of the step is a 10% improvement or something like this. Yeah, so this is not promising something which is not existing. This is really applying in very good engineering what has been developed over years, some things at Tesla, some at other companies and so on. But this is what is realistic engineering.
I want to give an example of those because this came from another battery science interview I did, and that is dry coating versus wet coating of anodes. And the wet coating, an anode has to be coated. So if it's wet coated, as was done or is done now, it then has to sit in the factory and dry, which takes up a lot of floor space and time. But if you dry coat it, then you don't need that, and you've opened up a very significant percentage of your factory floor to other production, and that lowers the cost of the battery. Are those the kind of innovations that you're talking about?
Absolutely. But they are not only talking about this, they have acquired already years ago the company Maxwell, a manufacturer of supercapacitors. And the electrode production in supercapacitors is pretty much the same as in lithium-ion batteries. And they have developed the dry coating. So this is what I say. They're announcing technologies to come which have been already developed, maybe not applied to the lithium-ion batteries yet, but this is something which is known. There is experience, and there's manufacturing experience, there's commercial products to do so. And this is really something different from what we hear on these very innovative technologies, where step improvements must be done, which are not there yet, and there's a lot of risk in the market. And this is what I really like from this master plan Tesla showed. There's only one thing in the presentation which I cannot prove. This is, I understood that they are claiming for a full silicon anode. This is something I haven't seen yet. But all the other things can be done if you have engineering power and so on, no question. It's a great challenge, no question, but a challenge which is possible with good engineering. It does not require something which falls from the sky.
Professor Sauer, thank you very much. Very insightful observations about the technology, where it is, where it's going. Really appreciate it.
Yeah, it's my pleasure. Thank you very much.